Good afternoon, everyone. As I said, I'm Luke Madaus from Jupiter, and the title is Cloud-Based WRF Downscaling, and I will talk about that. I want to talk more broadly about what Jupiter is and what we are doing. So I'm going to start off with what Jupiter is, and then some challenges to running WRF at scale and how Jupiter has approached this problem. And it's going to be, I like where this talk is falling because I'm going to show how, as a company, we're trying to leverage a lot of the things that have already been talked about here. Not only cloud platforms, but the kinds of technologies and data formats Unidata is providing, analysis tools like the Pangeo stack and Python. We're bringing this all together, and this is kind of an example of how this can be done. We've heard about these tools separately. Let's put them together. I'm going to give a brief demonstration, very brief demonstration, about how running a container looks like. So some people have had questions about what is a container, what is Docker. I'm going to go over some of that later in this presentation, so hopefully you'll learn a little bit more, understand what that is. Talk about some example use cases, what we're doing with all of this data at Jupiter, and then wrap up with some how you can get involved, how you can use some of this container technology. And then I'm probably not going to take the entire period of time, but I have several questions at the end related to some of the topics that have come up here that I'd like to open up for discussion with the group, which is always kind of a risky thing with these relatively silent presentation rooms, but we'll see if we can get something going here. So, first, what is Jupiter? So what tends to happen these days, I go and introduce myself. Hi, I'm Luke Madaus. What do? I work at Jupiter. I love your notebooks. They're the best thing ever. I do all of my work in these Jupiter notebooks. They're amazing. So the most important slide of my talk is that these things are not equivalent. Jupiter is not, as we say, Jupiter, to emphasize the difference here. So forgive me if I keep talking about Jupiter notebooks during this, because otherwise it gets way too confusing for us to talk about it. So no, we are not the notebook company. We're actually a startup, began almost a year ago here in Boulder. The science team was comprised of several former NCAR, NOAA, government, and some private sector scientists. And to sum it up in this one quick little sentence, what we're trying to do is translate the latest in climate scientists to the needs of a diverse community of users. So summarize that kind of on this slide, we typically think about two different communities at Jupiter. One is the academic and research communities. There's a lot of really cool stuff going on. A lot of work has been done, particularly in the climate sphere, trying to identify how climate change is going to affect us on a very local scale. How is rainfall going to change in this location? Or how are heat waves going to change in another location? And this is great. We've got a lot of progress, a lot of methods, a lot of data that is generated. And if you're a researcher, you typically publish this publish this work in a paper in some journal. And then you turn around and go right back, and what's the next step in this process? And it just kind of sits there, assuming the journal is there, someone will find it, and things are good. There are some people who do make an effort to try to reach out and broadcast this information to a wider community outside of academia, and some people are very successful at it. But in our opinion, it's not done as widely as it needs to be, and it's not done as well as it could be. So, that's on the academia side. If we look over on the side of potential users of this information, like industry and governments, often these groups are despite you think of them as innovators in industry, government's not so much innovators, but industry can be innovators, they're still locked often into cycles of we have this data set that we use, we have these models that we know and understand, we have these methods that we always apply. And they'll cycle through those models, making incremental improvements, but are kind of reticent to include new, novel, potentially riskier information into these systems when they have deadlines to meet, budgets to match, and need to be able to show something safe and consistent. So what Jupiter's trying to do is fill this space in between them. We're trying to kind of take the best work that's coming out of the climate community and communicate it to industry and government in a way that's relevant to them, useful to them, and meaningful. And at the same time, we also want to take some of the new practices and emerging constraints from industry and government and bring them back to the academic community. Not only technologies like cloud technology or the cloud platform, but also questions of just what kind of information is useful to these end users, and how can academia then go and provide these kind of relevant information to address these needs. So we see Jupiter sitting at kind of this nexus of these three different areas, two of which I've already talked about. One is the research community, and one is the end users interested in climate risk. And we feel like we can fill this space because we spent a lot of time building a team of people who has a lot of experience in both of these spheres. As I mentioned, our science team is comprised of former NCAR, NOAA, government, and some private sector scientists. So we get it when talking to university researchers. We've all published papers. Most of us have gone through the university system, through the doctorate programs. We know how this system works, what you can do, what you can't do. We can communicate on that level. And as a complement to our science team, we also have an executive team based in San Mateo, California, with a lot of veterans of the Silicon Valley tech scene, including financial officers from several Fortune 500 companies, serial entrepreneurs from a number of tech startups that have gone on to do several $billion in sales and value. And because we have that team, that executive team can go to these industry partners, to these government partners, and they are known names. They're respected, and can get a seat at the table, and actually can get people to listen to what we have to say. So we've gotten a lot of experience in both those areas, and tying it all together is what we're calling our cloud native platform. So by cloud native, I mean Jupyter does not buy computers, except for our laptops. Like literally our office in Boulder, despite being heavy scientific compute intensive office, we have our one laptop each, and that's it. Everything we do is done on the cloud. And so we're trying to figure out how to do all the things we would typically do as atmospheric scientists or system scientists on the cloud, and then take that and translate it into a format that's useful for our end users. So that is a lot about what Jupyter does. And initially what we're trying to do is we've kind of picked two areas to crystallize our attempt to communicate changing risk with a changing climate. And we call these two products flood score and heat score. So you might imagine flood score involves looking at how the risk of flooding changes with a changing climate, and heat score is how the risk of extreme temperatures changes in a changing climate. And our goal is to be able to describe how these risks might evolve on a hyper-local scale, and also on temporal scales ranging from daily. We have a operational flood score prediction system that's currently in development that will be producing forecasts on the scale of hours to days in the future, out to long-term kind of downscale estimates of how heat and flood risks are going to evolve by the middle of this century, for instance. So when I say hyper-local scale for these risk estimates, what you should read in that is downscaling. That's the term we commonly use in atmospheric science community to talk about taking the relatively coarse scale data that we get from, say, a climate model or a reanalysis and bringing it down to a finer scale, not only just finer weather scale, but then running further downstream models to estimate how changes in the weather go on to actually get at the risk things we care about. It's not just enough to say, well, we're seeing more extreme precipitation. How does that precipitation actually translate to flooding on a local scale? So that involves running downstream hydrologic models, getting things all the way down to the actual hazard itself. You can imagine there are a lot of models that have to be involved in this process, a lot of expertise has to be involved in this process, but I'm just going to focus on one particular aspect of that, as was alluded to in the title of this talk, which is using the WRF, the Weather Research and Forecasting Model, to do this kind of downscaling. So I'm going to start now talking about what are some of the challenges to doing this at scale. So you might imagine we have a global scope as Jupyter. We're not just limited to one particular location. So we need to be able to do these kinds of downscaling simulations across the globe, spanning multiple decades into the future, getting down to very, very high resolutions. We need to be able to scale this very well. So historically, what have been some challenges to running WRF quickly and effectively? So WRF, though we're doing it for downscaling, it can be used for a number of different purposes, but it typically follows the same flow pattern for how we run WRF. We start with some kind of existing larger scale data set, because WRF needs initial and boundary conditions from something, unless you're running the global version of WRF, but I only know a handful of people doing that, and probably better off doing something else if you're doing that. So for the most part, you're going to need something for your initial boundary conditions. This is some large scale existing community data set like another numerical weather prediction model, or a reanalysis data set like Air Interim or CFSR. Or we can downscale from climate simulations themselves. The CMIP5 archive is a ripe target for that. A lot of people have done simulations taking those climate models and trying to run them through WRF. You can then take the output from these simulations and apply it to a number of different possible problems you want to solve. Maybe you're interested in case studies of particular events, looking at how the local weather evolved in a response to a particularly high impact event. Could be doing operational numerical weather prediction. We could be trying to run a regional ensemble forecast system, trying to run it every day at the same time every day, multiple different members all going at the same time, for instance. We could look at working on the model itself. For instance, I think I can improve this parameterization scheme, but I want to test it for a bunch of different environments. So I'm going to run WRF with different versions of WRF, different modifications made to the model, and see how that changes my output. Or as we've been doing it mostly for downscaling, that is looking at how climate projection in the future might, how the weather in the future from climate, as indicated by the large-scale scope of climate simulations, might evolve on a local scale. But there are challenges at all these levels. And this is not an exhaustive list, but some of the ones that we've had to confront and I know other people in here have also dealt with. Starting with these existing community data sets. Often when we look at climate simulations or reanalysis, the files are kind of designed for bulk downloads. You'll have one file that has all your variables in it, but just for a single time. Or you'll have one file that has all the time in it, but just a single variable. And so if I want to run a WRF model, I need a certain subset of variables, and usually for a limited period of time. But that can involve downloading these large data files that we really don't need and trying to get them all locally. It just gets very awkward very fast. Another issue is that these large-scale data sets, particularly in climate simulations, are distributed often in the netcdf format. We love the netcdf format. Everyone knows how to use the netcdf format pretty much. But WRF, for some reason, decides it wants everything in GRIB format or its input file. So that if you look online for like, how do I downscale a climate simulation, there are often these convoluted recipes of run wgrib and then do this other NCO operator and then crunch the file in this way and do the transformation. That gets us into this variables not in the right format thing, where, for instance, from a climate simulation, you might have the data stored on the raw model levels, which are some weird hybrid of pressure and sigma and craziness that you have to then undo and put in something that WRF can understand. There's a lot of work just to get these existing data sets into a format that can be used for WRF. Then there's the WRF simulation itself. One thing I have to say right off the bat is tip of the hat to the people at NCAR. WRF has gotten a whole lot easier to compile than when I started using it like a decade ago. Now it's gotten pretty straightforward. The libraries have really matured and standardized, but it still can be a bit of an issue, particularly if you want to move WRF from one system to another. If I've got things set up, I'm running great on Cheyenne, but then, well, I happen to get this grant that wants me to run it on some other cluster, well, then I have to recompile everything and figure out how to make that work, and things might not match up. It's not necessarily the most portable. What if you want to do some of the experiments like I was talking about where you're trying to improve the model by changing the model code? It'd be nice in that case to keep a version of the model around that is the base unmodified version, maybe another version with your stage 1 modifications, another version with stage 2 modifications. Trying to swap these in and out and point your scripts in the right place to make sure they're doing the right thing, that can be a big hassle. And it's a lot of effort. And then finally, we can say you can get this to run at scale and generate a lot of these WRF output files. How are we going to share all this data? Because often you're not the only person who needs to look at this. You're collaborating with other individuals who often span not only the country, but also span the globe. They all need to have access to this data. They need to do some kind of analysis on it. Right now, you could start up your own file server, host it, find some, more and more people are moving to the cloud. This is not as much of an issue as it was before, but it's nice to have some kind of central repository that you don't have to worry about, you don't have to maintain to put this data so that it can be used by a wide variety of users. All right, so how has Jupyter gone about doing this at scale on the cloud? That's what we're going to move to now. So this is a wiring diagram of how Jupyter kind of visualizes its platform. And I'm going to walk through each of these steps in a little bit of depth to explain what we're doing at each stage of the way, and particularly how we've been leveraging these different technologies we've been hearing about over the past couple of days, and probably we'll hear about again the next day, to make this thing all come together. So starting with, I kind of focus this around the WRF modeling chain. So this is a very idealized view of the Jupyter platform. So I'll explain a few areas where this is kind of an oversimplification. But first we start with our data sets. Again, we recognize this idea that a lot of what the weather and climate community is producing right now is in netcdf format. And so we've, at our first pass, initially chosen to focus on technologies that can deal with netcdf format in a nice way, both for our locally held data sets and for potentially remotely hosted data sets. We put in front of those data sets some kind of interface to them that allows us to access them. In this case, I'll talk about we're leveraging thread servers, which is technology developed at Unidata, to allow us to do that kind of dynamic subsetting I talked about that's really crucial for doing these event-based WRF simulations. Once we have that input data, we can feed it into containerized geophysical models, and I'll explain more about what containerization is in the subsequent slides. And when I say geophysical models here, this is one case where I mentioned this diagram is somewhat of a simplification. As I mentioned, to do our flood hazards, it's not just running WRF, it's running WRF, feeding that into a hydrology model, feeding that into a hydraulic model, feeding it into an urban stormwater model or something like that. These are all chained together in some workflow that we've developed on the cloud. And then finally, when we have our output data, being able to analyze that and draw new insights, new conclusions from that is very important, so we can run these kinds of analyses on the cloud using two different techniques that I'm going to touch on a little bit. One is, again, leveraging containerization to build some standardized post-processing suites that we can just run, snap of our fingers, and it's done across a wide number of data sets. Or doing some distributed interactive analysis, and for this, we're leveraging the Pangeo stack that we heard about from Joe Hammond yesterday. I should mention throughout all of this that right now we're centered on Amazon Web Services. So if I mention certain specific cloud technologies, or cloud platform services, I should say, like S3 for storing data or EC2 for a compute instance, I'm just referring to the Amazon form of that. Most cloud providers have an exact analogy to most of these services. All right, let's go through this in a little bit more detail. As I mentioned, NetCDF format seems to be the current emerging standard for the industry, so we want to take advantage of that as much as possible because NetCDF has a lot of nice features. It lets you subset the data dynamically. It's a self-describing data set, so the metadata is all included. Most of us here probably have experience with NetCDF files. We know and love them. Our models mostly like them. And so one of the things that we have noticed is not only are we interested in using data in the NetCDF format, but as the community has hosted this data in NetCDF format, we don't have to necessarily do some kind of transformation to get the community's data into our system. We can leverage a lot of remotely hosted data sets, which are also using this similar DAP interface or thread server, as the kind of exact implementation this is called, so that we don't have to download all the data ourselves. I'll show this on the next slide, but there's a number of groups out there that are hosting their NetCDF data sets on a thread server, and we don't have to worry about how do we access this data. It's all there spelled out nice and cleanly through a common interface. As I mentioned, this lets us do on-the-fly subsetting. It minimizes our download size. But one key point, and I'm going to come back to this again at the end of the talk as one of the things I want to talk about, the way that data is stored on the cloud, as Locke was talking about earlier today, there's this idea of separating the compute from the data. The data is stored in something called object storage, and it's not a disk that's sitting connected to your computing unit. So every time you spin up some compute unit, you have to get the data, somehow access that data from object storage. And at the moment, NetCDF is not the best format for doing that. It's, for the most part, all you can really do right now. If I want this NetCDF file to somehow be input into my model, I have to lift it up and copy down the whole file again, which is kind of one of the things we were trying to avoid in the first place. So again, there's a lot of discussion I think needs to be had. And we've talked to a number of groups who are looking into this, who are concerned about this, about is there a better format for this community to be storing their data to make it more cloud-friendly and cloud-usable. I mentioned up there, one of the ones we've been exploring that Joe Hammond talked about is called ZAR. It's a very modern, cloud-friendly format. Right now, our biggest obstacle to using is just it takes a lot of effort to forklift all this NetCDF data and transform it into this ZAR format. We'll talk about this a little bit more at the end. As I mentioned, a number of groups already have these nice DAP-fronted data sets using threads. I've showed 3 examples here, one from NASA, one from NOAA, and one from here at NCAR. Unidata is hosting it. So from these 3 sites alone, you can't really read this up there, but from the NASA thread server, you can access a number of reanalysis data sets down to 6 hourly output. MERA 2, JMA only has monthly data, Array Interim, CFSR, and 20th century version 2 reanalysis. So do we need to bother to host a reanalysis data set when it's all up there available for the taking? Probably not. NoASRL hosts another set of reanalysis data sets, including some other useful, interesting data sets like pre-downscale or climate model output that's already been downscaled using existing statistical methods. And then the Unidata thread server hosts a lot of operational model output. So from the NCEP suite of products, a recent archive of their output is available through that thread server. And there have been a number in previous Unidata tutorials about how to use thread servers, and there are a number of notebooks out there, Jupyter notebooks out there, to show you how to read in that data. And so we kind of took that and brought that idea into our WRF container. I'll talk about that in a second. So, WRF container, what does that mean? We've got that input data now from a thread server, or just downloading it if we need to. We now are ready to run our containerized WRF model. So where did this containerized WRF idea come from? Well, the original idea came from an NSF-sponsored work called Big Weather Web. It's actually still ongoing, which funded a number of projects to explore how modern weather data processing could be expanded at scale. This includes things like funding some regional ensemble systems, doing machine learning work up at Colorado State, and as one component of it, this idea of containerizing our models. This work has then been taken by Unidata, and as we heard on the first day, they've been able to containerize a large number of the products that Unidata has produced. A number of models, a number of even the thread server itself, that whole technology has been containerized. And so this has really taken off. I'm going to explain in the next couple of slides what that means, what containerization means in more detail. But it's been a really nice technology that we're happy to use. Getting back to taking this data in netcdf format from all these things. As I mentioned before, one of the challenges of running WRF is that you need that data to be in a format WRF can understand. And right now, netcdf, for some reason, is not one of those formats. So we wrote a whole Python suite, rather I wrote a whole Python suite, to take an arbitrary netcdf file with known variable names and coordinates, and it will dump it straight into the WRF intermediate format, bypassing this whole ungrib and crazy phase, whatever middle steps, which lets us really, really quickly, surprisingly, go from I'm downloading this input data, it's already in WRF format, WRF can run with it. It's really, really nice. I'm glad we took the effort to do that. And it's one of these things we can do as we develop these containers is include with the WRF model codes like this that make the whole process a whole lot easier. And so it all gets packaged into one nice container that can then be easily distributed. One of the advantages of doing these containerized models is that it lets us leverage a lot of cloud technologies that are already in existence that expect containers as an input. For instance, on Amazon, they have a service called Batch, which works a lot like a queuing system you'd see on Cheyenne or some other large supercomputer. Instead of having a specific job, run script or anything, though, we just say, here's my WRF container, here's the commands I want to give to the container, run this container whenever you get a chance, or something like that. We can specify our queues to only use compute instances of a certain size, a certain memory requirement. We can specify a priority, whether we want to wait for the prices to drop a certain level when we want to run it. It gives us a lot of control. But the idea is we can just say, with a couple of lines, here's 5,000 simulations I want to do. Go grab the containers and run them without having to do a whole lot of setup. It's really nice. Even with that said, we still are pushing some of the computational limits of current cloud compute architectures with this technology. Kevin showed the other day from Amazon, they've been trying to scale WRF going up to lots and lots of instances. And you can do that. It's hard to do that, though, in a containerized environment. So there are some drawbacks to using containers right now, and that's particularly if you're trying to do MPI sorts of calls across instances, trying to get the containers to work together can be done, but it's not the most intuitive or easy thing to do right now. So we're constantly working we have ongoing work with groups like Docker to try to figure out how to better use this containerization technology at scale in that way, as opposed to at scale, I'm running multiple versions of this model across many different instances. So I've said containerization now a ton of times. What is containerization? That's probably a very important thing to answer at this point. So I like to think of containerization as taking everything you need to do a particular task and wrapping it up in one nice little package that can then just be run anywhere. A container is a portable, self-contained, only what is needed package that can perform some function that you need to perform on any machine that is running what's called an interface layer. And probably the widest used interface layer right now is something called Docker. You've probably heard of that. When people talk about containers, it's almost become synonymous with Docker, though there are other companies out there that are doing this kind of containerization. And so the idea behind something like the WRF container is I take a single file, it's just a text file really, and I make a list of all the things that I need to run WRF. In this case, it could be, what operating system do I want to use? We'll pick a lightweight Linux operating system, for instance, because that's all WRF really needs. Pick what libraries we need. We don't need every single library under the sun, we just need the specific things that WRF would be using, like the netcdf library or MPI. We pick compilers that WRF needs. G-Fortran and GCC are free, easily available. We can add that into the container. We then go through and run through the whole compile sequence for WRF. It builds this executable within the container. And then we add in what other things we think are needed for this WRF run. We could add control scripts, which tell the container how to execute the whole WRF sequence. We can throw in analysis scripts to do something with the output once the output is done. And then we just package that up into one nice little unit called a container. And one nice thing about containers is they're very easy to distribute to a wide number of users very quickly, very simply. And there's two ways you can do this. One is after you've built a container, you can push it to an online repository, just like you would push your code to like GitHub or something like that. And then it's the same kind of push and pull syntax works for containers as it does for your code. If I see someone has posted a WRF container, for instance, this is the original big WeatherWeb NCAR WRF container, all I have to do, as long as I have Docker running on my system, is do Docker pull the address to this container, and it will pull that container image down. It's there ready for you to use. With that said, container images can get to be large and somewhat large in size. I think our WRF container is a couple of gigabytes. So if you were experiencing problems downloading DJ's 3 gigabyte data set earlier today, you can imagine if I have to do this hundreds and hundreds of times every time I want to run something, maybe that's not the fastest way to do it, but it is pretty useful. The alternative is, as I mentioned, when I went to build that container, I just wrote a single text file that was a list of instructions of this is what I need for WRF to happen. In the Docker world, that's called a Docker file. And this is an example of one that you can't read because it's really blurry up there. You can imagine this Docker file, it's just a single text file, a couple of kilobytes. And it has line by line, it basically just says run this command like you're in a Linux environment. So run yum install all these libraries I need. Run wget the Anaconda distribution of Python so we can use that. Run install these Python packages. You then go through and run the WRF compile sequence. Give someone this couple kilobyte text file, and as long as, again, they have Docker installed, they can run the command docker build this, and it will do all these download things and build a container for them right on their local machine. So it's very easy to distribute this kind of software in this way. What we can then do is then wrap this container, because it is one complete unit, and we know where everything is in that unit and how it works, we can wrap that up in, say, a Python object, so that when we're online wanting to submit these simulations, we can very simply configure our container to do what we want to do and send it off to, say, a batch queue on the cloud to just run all these simulations we want it to do. Again, you can't really read this, but this is basically what we've been doing in Jupyter, is we have a little Python kind of a shell, an object that wraps the command to run this container. And all I have to do is import that object. That middle cell there is setting just a Python dictionary of a bunch of parameters relevant to this run, like what do I want to name it, what's the start time, end time, where should I get my initial and boundary conditions from, what queue do I want to submit it in, how many processors is that going to require, what version of the WRF code do I want to use, what nameless configuration that I have saved do I want to use, and then just send that dictionary to the object. We can use the cloud APIs to estimate how much this run is going to cost on the cloud. So it can look at the duration of the run, and we've built up this large library of simulations I'll show at the end, so that we know approximately if your simulated domain is this size, you're doing a simulation of this long, it'll probably take this long to run on the cloud. We can grab the latest pricing arguments to say pricing values from online and say this is how much it'll cost you, and then just submit it to the queue when you're ready to run. And the output of this simulation is dumped immediately to cloud-based object storage, which can be made public. You can access it just from your laptop through a browser. Really easy to get at the data once it's there. So I'm going to do a quick demonstration of this, which involves leaving here. So I could show you how to do things on the cloud. Problem is, one, it's a really boring demonstration because it's like, submit. And then, great, there's one thing in the queue, and there's a number 1 there. Okay, great. And also, there's a lot of, so we have this whole infrastructure built up, like I said, to use these Python objects to submit to the queue. But currently, Jupyter only works if I'm behind our Jupyter firewall. So we're going to be doing kind of a basic level demonstration using this existing NCAR big WeatherWeb WRF container. So I'm on my Mac here right now. And as I said, it's really easy to get a container image. You can just pull it from Docker Hub if it's been posted to Docker. The command I'm about to enter is not going to work for anyone, though, because we are mirroring something on Jupyter's, again, internal page. But I'm just trying to illustrate how simple this can be to do this. So here I'll put in shell. I can do this Docker pull thing, and I already have the image up to date, but it basically went out to our server and said, is this container image exist? And it would have pulled it down if there was something different. So now that that's all it takes to get the container installed on your system. And then what I can do is run this container. It's a command called docker run. And I'm going to give it a couple parameters. So what I've done here is docker run. Minus remove means when it's done, just remove all the containers data. I don't need to keep it around. Minus IT opens an interactive terminal, which means it'll scroll. It'll show us the output instead of hiding everything. Then I have the name of our container. In this case, the name matches the repository I pulled it from. And then we just give it a command that we want to run in the container. And so it's a Python script that I want to run. I know this from looking at the documentation for the container. It's called runwrf.py, which will run the sequence. This particular container has a baseline case included in it. That's a simulation for Hurricane Sandy. So I'm telling this container, run this script with grabbing the Sandy baseline data. And then I have to tell it to run ungrib in this case because we're actually running ungrib. If I did everything right, it now will just running here on my laptop, do all the pre-processing, went through ungrib, metgrib, real e.exe completed. If any of you run the WRF sequence, these are all familiar things to you. And now it's running on my local machine using 2 CPUs. This is a really coarse, really short simulation. Again, it's just for baseline testing purposes. So it's like a 40-kilometer grid spacing over the Western Atlantic for a 3-hour time period as Sandy was spinning up. But I can run this on my laptop. It'll finish in a few seconds here. And then we will show something that, of course, now it takes longer than it normally takes to run. Yay, it completed the interpolation time. Success, complete WRF. That's what I always like to see there. So one of the things I want to point out now is like this directory I was in, there's nothing in there. If I look at output, there's nothing in there. Because that's one of the both benefits and downsides of containers. Unless you tell the container to actually interact with your system, the container is a standalone object with its own self-contained operating system and self-contained everything. So I can run this whole WRF thing on my machine. It'll use my CPUs, it'll use my RAM, but it'll do nothing to my hard disk. So I'm not overwriting any files, nothing gets lost, nothing gets mixed up. It's all self-contained. But what we can do, and this is another kind of flexible, nice thing about running these containers, is we can expose certain parts of our system to the container. So I'm going to put the path to my directory here, WRF test, output. And I know from, again, the container documentation that all the WRF output in the container is written to a directory in that container called /WRF output. And we'll run this whole thing again. Again, it'll take a few seconds. But the idea is we can expose just selective parts of our current operating system. Not only is this useful for capturing output, but say that I'm trying to develop some code here to run a Python script or do some kind of analysis on a data set, but it requires downloading and installing certain tools that have to be compiled or whatnot. You can compile everything and build all that in a container and then say expose one directory in your container to a corresponding directory in your local system. Then with that container up, work on your local system, edit your scripts, and then run all the stuff, use those scripts to run stuff in the container while you're editing on your local machine. So you're not messing up your system by trying to compile stuff and overwrite stuff and do all that crazy stuff. That's all nice in the container. It goes away when you're done. But I can still be interactively editing scripts, making changes, and testing how that works as I submit them to the container. So the simulation went again, and now hopefully if I look at output, there's output there. Hooray. We had a successful WRF simulation. You can look at this if you want, doing all of our. So this is, again, this is just a simple 2-meter temperature or something. Come up here, use NCQ. Hopefully people can recognize, ooh, it's the Southeast Atlantic. It's only 3 time periods. You can see the hurricane starting to spin up there in the temperature field. Hooray. The idea is, yeah, you can just run. It took me no effort to get that simulation running locally here on my laptop. I didn't have to compile it. It's all pre-built, pre-installed. Just to another way of doing that, here I am SSH'd into an Amazon compute instance, right here. And I can Actually, we'll go back over here to save some time. I already have that container image pulled up there. Of course, everything's all hidden now behind all this. And I can just go to this Amazon compute instance that I just logged onto, do the Docker run command there where we pull the container, and it works right out of the box right there. The idea, again, it's very portable. All I have to do is pull the container down, run it, whatever machine I'm on. As long as it's running this Docker interface layer, we can make WRF work. And at the end, I'll have a link to where the original NCAR, the big WeatherWeb NCAR WRF container is if you want to experiment with that a little bit more. But for now, let's get back to this presentation. All right, so I just kind of showed how we're able to take this containerization technology, and you can imagine distribute it very widely at scale on the cloud. So we generate all this data by running all these WRF simulations. What do we do with the data once it's done? There's a couple things we can do. One thing I mentioned is we can, again, leverage containerization and package post-processing suites in the same way. So for instance, the MET, Model Evaluation Tools package, it's also been developed here at NCAR. We have that containerized, and we can use that, apply that on our model output to evaluate it. Again, apply standardized post-processing methods to all of this output. All very easily shareable, very easily scalable. But the other thing, as a scientist, thing that I'm more interested in is being able to do more interactive analysis. You know, I want to pull this data in, actually get a feel for it, look at it, make some calculations, explore how different variables are related. And what we've been doing a lot of recently is leveraging what's been developed through the Pangeo development team. That's this stack of programs, as Joe Hammond talked about yesterday, includes the Jupyter notebooks, the Dask library, and Xarray. This has given us a lot of, we've had a lot of success implementing this system. Not only because it too can be containerized, which we love to do, but the Xarray team, the development team for Xarray in particular, has done a lot of work to really make it nice to work with a wide variety of the kinds of gridded data sets that we use in the geosciences. As I mentioned, we're not just running WRF, we're running downstream models. And it turns out a lot of the hydrology and hydraulic models we run output in a format called GeoTIFF, or some kind of a TIFF file. But unfortunately, Xarray reads in TIFF files just like it reads in netcdf files. And so we've been able to do all of our analysis using this single Python environment, which has been really nice for us. Furthermore, when you couple it with the distributed capabilities of the Dask library, like Joe was showing us the other day, it lets us perform a lot of calculations in parallel at scale without having to worry about the fact that our data sets are quickly blossoming to tens to hundreds of gigabytes in size. And when we do our flood calculations, as I'll show at the end, we get down to 3-meter grid spacing over an entire urban area, which gets, these are fields that are thousands by thousands by thousands of events. And it's really, really challenging if you had to read all of that, try to do that all in memory without chunking up the file into different sections. But by using these kinds of Dask distributed tools, it lets us write a simple script to say, this is what I want to do to all the data, and then let Dask handle the scheduling and the dividing and figuring out how to do that. It's been really nice. And so we're starting to engage more with the Dask, Pangeo development team to decide how can we make it better, how can we in turn contribute back to it as problems and needs arise from our use cases. All right, so what are our use cases? Some things we've been able to do with this data. As I alluded to, one thing we've been able to do is run extensive WRF benchmarking tests across a wide variety of cloud resource configurations. As Lack was showing us earlier today, on the cloud, it can be trivially easy to just say, I want 8 CPUs and I want 8 gigabytes of memory. Give me an instance for doing that. But there are a lot of things at play when you're doing things in the cloud. One is we have this flexibility, so we're not just confined with, well, I have 64 CPUs in my cluster, I guess I'm going to use 64 CPUs. We can try to actually pick and choose what's going to give us the best combination of memory and CPU, and also scaling that by how much it's going to cost us. You might think that, for instance, just getting one instance of the biggest and best thing you can get, which will get your model done the fastest, is the best thing to do. But when you start scaling out with how long that model simulation takes and how much it costs per hour to run that simulation, that's not always the best case. In fact, we've actually found it faster in some cases who run some of these larger simulations on much smaller instances. Sure, we're willing to wait an additional 20 minutes for the simulation to finish, but it saved us a fair amount of money when you aggregate it over these thousands and thousands of runs. So there's a lot of more economical decisions you have to make when running on the cloud as opposed to just, well, this was enough CPUs to cover my simulation or enough memory to cover my simulation, I'm good. And so we have a pretty big library now of all these different combinations and what they cost, how long they would take. Kind of a blurry plot here. We're just showing kind of examples going through different combinations of CPU types and memory amounts. Because we have access to so many data sets, reanalysis data sets, climate model data sets, it becomes really easy to do comparisons across these different data sets and to even develop quasi-ensemble type estimates just by changing the initial conditions, by changing the source we're getting them from. So here's an example case. When we were looking at a flood score, one of our first target cities was Charleston, South Carolina. We had a client there who is a property management company. They buy a bunch of warehouses or property and erect warehouses, and they lease these out to their other various customers who need them. And so they're very interested in very specific locations of what's the risk of flooding at this location, what's the risk of flooding at this other location. And Charleston, South Carolina, you get a lot of hurricanes. It's one of the major sources of significant flooding farther from the coast. So we simulate a lot of hurricanes, both in idealized sense and actually using real historical cases. So this is an example where we looked at Hurricane Hugo, which was arguably the most significant tropical cyclone event to impact the Charleston, South Carolina area in recent memory. And we could run one Hugo, that's great, but when it comes to estimating risk, it's all about how much we can sample and how many different scenarios we can play out here. So what we found is that by choosing different reanalysis data sets, same time period, same storm, you actually get very different responses to how the hurricane is forecast to evolve based on just this reanalysis data. So you can see for a major hurricane at landfall, this shading in the background is on the wind speed at 10 meters. Some like Mira and CFSR had some pretty strong wind speeds, and they also lined up fairly well with the observed track, which is that white line with the dots on it. Other reanalysis data sets, just out of the box without doing any kind of tuning, didn't really line up as well. NAR in particular, we've had a lot of problems with NAR. Just throwing that out there. It didn't line up very well. It didn't produce a very strong storm. But the nice thing is this was, as I kind of showed in the previous slide, 10 lines of Python. Say, I want to do all these simulations, just swapping out just a list of these are the kinds of initial conditions I want to use, loop through them, submit them to the queue, and they're done. So it took like 1 minute per simulation to do the whole pre-processing sequence, which meant going to these thread servers, grabbing the data, converting it to the intermediate format, running through MetGrid and Real in WRF. And then the WRF execution for these 5 daily simulations, we nested down to 3 kilometers. There's actually 3 nests in here going down to 3 kilometers. Took about an hour and a half running them on the particular cloud instances we chose. And as I mentioned, it's 10 lines of Python for us to set this up and going. So let's just do a lot of these experiments really quickly, really easily. As we build up these simulations over time, not only from hurricanes, but also just from significant precipitation events, coastal flooding events from non-tropical cyclones, which are becoming a more and more frequent concern in Charleston, South Carolina. You get just unusually high tide is starting to flood inland areas as local sea level is rising. And so we're trying to simulate how those events are going to evolve as well. We can combine them all together and look at how how precipitation and the subsequent flooding are evolving in a lot of multiple climate models at once. So I mentioned that we not only hook into reanalysis data sets, we also can hook into climate simulations. And one of our pilot projects we've been working with on NCAR is hosting a data set called the CESM Lens, Community Earth System Model Large Ensemble. This is actually an ongoing cooperative effort between CISL and some people in CGD and us at Jupiter to explore how we would host some of these larger data sets on the cloud. So right now we have a select group of variables that have been, in many cases, subsetted down to North America. At least with their big, giant 3-dimensional variables, they were subsetted. But there are some global variables that are all on Amazon S3. They're not public-facing yet because we're still working out the details of how that works. But there are plans down the line in the next couple of months to start making this public once we work out some kinks. But because we have these data sets available to us, we can then use them in the same way we're using the reanalysis data sets to drive WRF simulations and do our bias correction, run our downscaling simulations, and look at how precipitation might change in the future. So this is just using 10 members of that CESM large ensemble out of 40 total. And we can look at this chart as showing the number of events per year where we exceeded 30 millimeters in 24 hours at this particular latitude and longitude, which is downtown Charleston, I think. And so you can see that this analysis shows that, yeah, by the end of century, once you start getting 2030 to 2080, you'd see a pronounced uptick in the number of these events, which is consistent with a lot of the literature for precipitation increasing in this particular area. But to develop just this simple plot, this took thousands of simulations of extreme precipitation. I think the total ended up being something like 5,500 simulations. And this is not just WRF, this is also the downstream hydro models. We got this all done in one weekend because we could just submit it to the cloud in batch, and they all ran. And this is kind of the output in graphical form. As I mentioned, we're getting down to 3-meter spatial resolution with these outputs. So this is a map of flood risk, actually current flood risk, 2018, the 1% chance of exceeding what we call combined surge, which is both the storm surge and the waves on top of it, throughout Charleston in a given year. And so these different colors correspond to what that 1% level is in feet above the ground. And so you can see, yeah, we can do these incredibly detailed simulations, these incredibly detailed estimates of risk by doing a lot of these simulations and then post-processing the output. This is what our pilot project looks like. That's what we're doing here at Jupiter. But one of the things about Jupiter is that we don't want to be the stereotypical private sector company that's all closed. We have our intellectual property and we don't want to share. We have some of that, but we're not trying to develop all this stuff in isolation. There's a big community of users out there. You guys are a big chunk of that community who are interested in the exact same problems we're interested in. How do I make my data scale? How do I do these kinds of analyses using Python, using these distributed tools? How do I do these things on the cloud? And there's a lot of choices that have to be made going ahead. And so we really want to engage with this whole community and open up whatever we can for not only input from the community, but also for the community to use some of the resources that we're developing, some of the methods we're developing, some of these data sets that we're planning on hosting, and try to collaborate in the best way possible. I mean, we're going so far as we even have an arm developed that does, we're evaluating sponsored research opportunities. We have a pilot program with Columbia right now where we're funding research into idealized hurricane track generation, which is very relevant, as you might guess, to our flood scar product. And we're always on the lookout for potential opportunities where we can develop tools that both help what our end users want, which is things like flood risk and heat risk, but also can help some people do things at scale that they might not have envisioned doing before as they explore these new ideas. So with that said, some things you can do immediately. As I showed that WRF container there, the big WeatherWeb project is NSF funded. And so there is a publicly hosted NCAR container, both the container image, which is on Docker Hub, which is this docker.com address, under Big Weather WRF. I should mention that that container image has not been updated for about 1.5 years, so it's a little bit out of date. However, if you are interested in doing your own stuff related to that container, as I mentioned, the other way to distribute them is to take that Docker file, that simple text file that's the recipe. That's available on GitHub at this particular address. And I believe that's what the NCAR, the tutorial people here at NCAR use for the WRF tutorial to build the version 4.0 WRF container out of that. But with that said, we carried, so the original people who developed the containerized WRF with that NSF grant are actually now at Jupiter. They're part of our science team. And we carried some of that money with them to develop this containerized WRF. So Jupiter is going to release its own version of the WRF container, which has been really souped up and streamlined, and I worked a lot on it, so that's why I'm kind of happy about it. But it includes things like that code for going direct from an SCDF file to a WRF intermediate format and bypassing this whole GRIB step. And also just includes the baseline cases and hooks for pulling reanalysis data from a couple of these thread servers online. So we're planning to release that sometime in the early fall, the exact timeline to be determined. But that is coming, and we will publish that when done. So as I just mentioned, our Jupyter containerized WRF was targeted for an autumn 2018 release. And we are starting, as I said, to open up our platform on a project-by-project basis for people to explore, how does my model run on the cloud? I have some idea that I want to test at scale. I want to use some of these DAS distributed clusters to try doing a particular analysis technique, with the caveat that we're very much predisposed to things that are immediately relevant to the products we are generating. Let me know if you think you have a good use case, and we're certainly happy to talk to people about ways they can potentially use our platform. And so this is my last slide. I'm finishing up a little bit early, but I wanted to leave some time for some talk about what I think are three of the biggest pressing issues that I want to hear back from this community. One, I titled it Cloud Optimized NetCDF, but it gets back to this idea that the NetCDF format as it is right now not the best for storing data on object storage on the cloud. As I said, it's not set up in a way that the way you access things from object storage now can subset the data easily or do things like that. So there seems to be, at least for us, an ever-growing need to figure out what do we do about this. We've been kind of asking if there are any groups that are working about this. We hear there's a lot of interest, but there's a lot of also kind of passing the buck from people. We'll talk to cloud providers and they'll say, the community needs to come up with a solution, which I completely agree with. We need to do something that works for us and not have something prescribed on us. Talk to other people who say, yeah, we're happy to develop tools that'll work with this new format, but it really needs to be decided by some kind of unifying body in the community. Something like Unidata, for instance. So we're kind of hoping to have a conversation, or at least be involved in a conversation, hopefully with Unidata, on where do we go from here for cloud storage, and what we can do with our data sets. Is the solution to migrate our stuff over to other formats? We've been talking about, as Lack mentioned, GeoTIFF format has been, they've gone through a whole progression of optimizing GeoTIFFs to be cloud, they call it cloud optimized GeoTIFFs, which is where we got the name. GeoTIFFs are nice, they're kind of limiting in their structure. You could have 3 dimensions to them, basically, and that's it. Not as good with the metadata as well. And so it's like we could fork our data over and convert everything into some kind of a GeoTIFF format. Is that really what we want to do? A lot of cloud tools, like for instance, Lack was showing us the Google BigQuery stuff. You can query your data really fast and handle terabytes really quickly. Or Amazon's SageMaker tool, where you can run these machine learning models right out of the box. Our biggest problem right now is our data is sitting there in NetCDF files, and we have no good idea of how we really want to transform that into something that can take advantage of all of these tools that are being developed on the cloud. We don't want to take our NetCDF files and turn them into one giant SQL database, because that just seems like a silly idea. We could, but is that really what we want to be doing? I think we should have a conversation about this. So that's one question I want to throw out there. Another has to do with the containerized warp simulations themselves. As a cloud-native company, we have a clear use for these as we're trying to run our stuff in the cloud. For people who have access to things like Cheyenne with a precompiled WRF there that's always being updated, do you have a need for this outside of the fact that Cheyenne is down 25% of the time and it'd be really nice to move stuff over to the cloud when you needed to? I mean, do you think a containerized WRF simulation is useful for your workflow? How do you envision this kind of thing integrating into what you do? And kind of parallel to that, if you were to use it, what features would you find useful in a standalone containerized WRF model? And then finally, just a more broad question about cloud-hosted data sets and these data proximate workflows. As I mentioned, Jupyter is hosting some data sets. We're planning to open them up to the public. And people like the science communities at Amazon and at Google are also hosting data sets. And we're kind of curious, what data sets would people most use if we put on the cloud? What would it take to get people to start adopting these technologies more and more as they are growing? Like if there was some magic data set that if this data set was there, well, absolutely, that makes all the difference to me. I'd run my stuff in the cloud. Or if we had these particular models containerized, that would be great. Then I would be able to do all this stuff on the cloud. Open up to discussion. So that's my last slide. This is my contact information. Again, I'm on Twitter at Madaus. You can go to our website at jupyterintel.com to find out more. Though I'll caution you, it was written by business people. And business people use fancy non-scientific words. So just caveat out there, we don't actually sound like that when we talk. And then my email is at luke.madaus@jupyterintel.com. So I'll wrap it up and take any questions.
Are you saying there's some problem when you run on the cloud with hitting create IP or open app online source? Is the cloud hidden behind a firewall or something?
No, that was for to access the Python protocols that we have. I said we'd wrap this container with like a little Python object. Let's just call it. For me to run that call and submit things to the queue, I have to be behind Jupyter's firewall to be able to submit that thing, otherwise it'll block me. So it's our own little security thing. But to that point about the thread servers, we do note that if I submit 5,000 WRFs at once, all calling the create IP thread server, it does slow down very much so. So we've been rationing our usage of that. Because we'll hit these with these bursts, but we don't want to abuse these data sets, because it is a public service. And to that end, we have pulled some of these larger data sets, like a particular reanalysis data set that we're using a lot, behind our own, in our own, actually our own thread server hosted locally, just to avoid, for like a lot of these simulations we want to do over and over again, we don't need to be hitting all these different reanalysis data sets. We've picked one we think is working well for us. We don't want to hit these servers all the time. So that's there. Well, I just bring that up as there are a lot of people, distributed users out here who, yeah, if you want to do a one-off WRF simulation, well, it's really easy to just pull that data down and it works for you. Yeah.
Yeah, you mentioned the WRF is most models and data sets are always being revised. How do you deal with that in terms of the containerization? How much of an effort to keep up with the new versions?
Right. So, I mean, with that Docker file that gives us the build instructions, we can. I mean, it's very easy to rebuild the container at any point. So you can, if one of our libraries that's supporting WRF gets updated, you can just rebuild the container, and as long as you're grabbing the most recent version, it'll grab it. Same thing with WRF. We have it programmed in there that I can just change 3.9.1 to 4.0, and it'll pull the latest WRF. One nice thing about the containers as well is that it works kind of like GitHub in that, or Git in that you can tag different versions of a container. So I can tag this as, this is the WRF 391 release, and that's there. It's preserved forever as a working version of WRF 391. Then when I build WRF, I can go and make the changes needed to build WRF 4, rebuild it, tag that as WRF 4. And so we can keep a whole big long stack of previous versions should we need to iterate and go back between them. But it's pretty easy. Yeah.
Have you looked at using JSON documents in a NoSQL database as a format for storing weather data?
We have. We've, for instance, been taking the GHCN data, it's a daily weather observations from the globe, and we have put that into an actual database form, a SQL database, and have that kind of keyed into our system. It's just testing how well does that work for something that lends itself to a tabular format like that. We have not tried doing anything with our large gridded data sets in a SQL database format or anything like that.
Not SQL, NoSQL, like Mongo or Couchbase.
Yeah, yeah. We have not done any database, or even with a NoSQL or any of the non-structured databases.